Okay, so we ran out of time to cover chapter 13.1 and 13.2 in class, but they kind of have the nice unique property that they're pretty simple sections, and so I wanted to go ahead and just give a presentation on them now, and you can watch the video. Like the rest of chapter 13 section 1, which I have on the handout you can see here, so I'm just continuing beyond the one we did in class, has familiar types of problems, and as we'll see in 13.2, we'll just be doing like derivatives and integrals. So it should be pretty basic stuff, I think you'll find. So in this example, the next one in class that we didn't do, here we're finding a vector equation and parametric equations for the line segment that joins this point, 1, 3, negative 2, to this point, Q, 2, negative 1, 3. So when we talk about finding the equation of a line, what we're interested in is what is a point it passes through, and we have two of them, and what's a vector to which it's parallel. So we can find a parallel vector. So our line is parallel to the vector PQ. Okay. For PQ, we're just going to subtract the components Q minus P. So taking the x of Q minus the x of P and so on. So 2 minus 1, I have 1. Negative 1 minus 3 is negative 4. 3 minus negative 2 is 5. So we have a line that passes through 1, 3, negative 2 and is parallel to this vector 1, negative 4, 5. So to get parametric equations, well, I guess we could start with the vector equation since it says find a vector equation. So for vector equation, we have r of t, and then I'm going to take my points, say 1, and add them to these coefficients of t. So I have 1 plus 1t. Next I'll go to y, so 3 minus 4t. Finally I'll go to z, so that's negative 2 plus 5t. So this is the vector equation. For parametric equations, I mean, all I'm doing is copying the components of my vector equation. So here we have the x, y, and z components in my vector equation. And so these are my parametric equations. Okay, so I have vector equation and parametric equations of this described line. For the last example, we're going to find a vector function that represents the curve of intersection of the cylinder x squared plus y squared equals 1 and the plane y plus z equals 2. So these equations are supposed to be true at the same time. One thing we can say, whenever we have an equation like this, where we have x squared plus y squared equals 1, that one's familiar. We recognize that sort of as a trig identity from trigonometry. So we could say if x is cosine t and y is sine t, then x squared plus y squared equals 1. So that's our cylinder. Okay. Now in the plane y plus z equals 2, we're looking specifically at where the cylinder intersects that plane. So at that point, y is equal to sine t. Okay. So at the intersection, we have sine of t plus z equals 2, since we have y plus z equals 2. Well, then z is equal to 2 minus sine t during the course of their intersection. Okay, so now if we want to write a vector function, we can just say r of t equals, all right, let's write the x component, so that's cosine t, and then the y component, that's sine t, and finally the z component, which is 2 minus sine t. So this vector equation describes specifically the curve of intersection of the cylinder and the plane. It doesn't describe the cylinder and the plane individually. I mean, on the cylinder, you could always parameterize as cosine t, sine t, but during the intersection of the cylinder and the plane, z is specifically 2 minus sine t. Okay, so next I want to move on to section 13.2. So here we talk about derivatives and integrals of vector functions. Really, this is a lot like Calc 1, honestly. So we're going to recall from Calc 1 that a derivative, say f prime of a, is the slope of the line tangent to y equals f of x at x equals a. The idea is similar for vector functions. R prime of a is a tangent vector to the space curve defined by r of t at t equals a. So I've got some curve C running along the page. Okay. I can imagine that I have a vector r of t that points at the point P, and maybe in the future r of t plus h points at Q. We can make a secant vector going from P to Q, okay, or at least with initial point P and parallel to the vector from P to Q. And that takes on that familiar limit definition, or at least the parts of the limit definition of the derivative. Normally in Calc 1 we'd see f of x plus h minus f of x over h. Here we see r of plus h minus r of t over h. Okay. As h goes to 0, so as we approach the point P, we're seeing the derivative. In Calc 1 that would be f prime of x, here it's r prime of t. Sometimes we'll see this in the future, mainly in 13.3 we'll see that. We'll consider the unit tangent vector. Unit vector just means the length is 1. So if the tangent vector is r prime of t, then the unit tangent vector would be r prime of t over its magnitude. And the formula for r prime of t is exactly what we would hope it would be. I mean, if r of t is a set of component functions, f of t, g of t, and h of t, exactly as we'd wish, r prime of t is the vector made up of the derivatives of those components. So in the first example, we're going to find the derivative of this function. R of t is 1 plus t cubed I plus t e to the negative tj plus sine of 2tk. And then eventually we'll find the unit tangent vector at this point where t is 0. Okay, so to find the derivative of r of t, we're just going to take the derivative of the individual components. So I have 1 plus t cubed prime times I plus t e to the negative t prime times j plus sine of 2t prime times k. We know how to do derivatives, of course, so I'm looking at 3t squared I. Remember that to get the derivative of t to the negative t, we're going to use the product rule. So derivative of the first times the second plus derivative of the second times the first in front of j. And then for sine of 2t, we would need the chain rule. So that's cosine of 2t times the derivative of 2t in front of k. And now let's clean this up a little bit. So I have 3t squared in front of I. And then here inside the brackets, I have e to the negative t, since the derivative of t is 1. The derivative of e to the negative t is negative e to the negative t, so I have minus e to the negative t times t, all in front of j. And the derivative of 2t is 2, so I have 2 cosine 2t, all in front of k. If we like, we could clean up the middle component a little bit by factoring, like we could take out an e to the negative t. I'm not saying it's necessary, it's another one of the, it's a fine line. I mean, it would bother me to leave it unfactored. Maybe you don't care. That's okay. So here I've factored out an e to the negative t. Looks a little bit nicer. So this is our derivative. In part B, we're going to find the unit tangent at t equals 0. So the unit tangent is r prime of t over its magnitude. We're interested specifically in the unit tangent at 0, so we want t of 0. So in other words, t of 0 is r prime of 0 over the magnitude of r prime of 0. Let's see, well, r prime of 0 comes from putting 0 in for t in all these places. So if I put 0 in for t on 3t squared, I'm going to have 0. So I'm not going to have an x component, or at least a meaningful one. If I put 0 in for t in the y component, well, I'd have e to the 0, that's 1, times 1 minus 0, which is 1. So all told, I've got just a 1j. Going on to the z component in front of k, if t is 0, I'm looking at cosine of 0, which is 1, so I have 2 times 1. So that's a 2k. Now we need to look at the magnitude of r prime of 0. Well, the components are, I guess you could say, 0, 1, and 2. So to get the magnitude, I've got 0 squared plus 1 squared plus 2 squared. In other words, what is that? Square root of 5. So I have 1 over the square root of 5 times j plus 2k. And we could distribute that 1 over square root of 5, giving us 1 over the square root of 5j plus 2 over the square root of 5k. So this is the unit tangent vector at 0. Okay, so going on to the next page here. Okay, so for this curve, r of t is the square root of ti plus 2 minus tj. So notice that we're on the xy plane. We only have 2 dimensions here. Find r prime of t and sketch the position vector r of 1 and the tangent vector r prime of 1. Position vector specifically meaning starting at the origin, because we could draw a vector anywhere as long as it has the right magnitude and length, but we're starting specifically at the origin because of the word position. So first let's find r prime of t. So we're going to find the derivative of square root of t and the derivative of 2 minus t. So just the derivative of the component functions. And so I have 1 over 2 times the square root of t in front of I, and a negative 1 in front of j, derivative of negative t there. Okay, so now I have my derivative. Now we're going to sketch the position vector r of 1 and the tangent vector r prime of 1. R of 1 is easy to find. We're just going to replace t with 1 in the original function. So that's square root of 1 times I plus 2 minus 1 times j, giving us a vector of I plus j. Or you could say that's the vector 1, 1. R prime of 1. So for r prime of 1, we plug 1 into the derivative here. So I have 1 over 2 times the square root of 1, I, minus j, since there's no t in front of the j. And so r prime of 1 is 1/2 I minus j. You could also write that as the vector 1/2 negative 1. And so now we can sketch these. So the position vector r of 1 will start at 0, 0 if we're starting at the origin, since it's a position vector, and it will end at 1, 1. So there's r of 1. The derivative, r prime of 1, will start at 0, 0 and end at 1/2 negative 1. So write 1/2 and down 1. So here's the vector r of 1 and the vector r prime of 1. Okay, so next let's find parametric equations for the tangent line to the helix with parametric equations x equals cosine t, y equals sine t, z equals t at the point 0, 1, pi over 2. So if we're talking about the tangent line, what we can do is sort of go off the tangent vector. We have a point that the tangent line passes through. So let's find the direction of that line by finding the tangent vector. The tangent vector points in the direction of a tangent line. It's tangent to the curve at that point. So if we say r of t is equal to the vector 2 cosine t, sine t, t, then the tangent vector in general is r prime of t. So that's the derivative of all these. Negative 2 sine t, cosine t, 1, just taking the derivative of each component. Now, if we're interested specifically at the point 0, 1, pi over 2, what we need to do is figure out what vector do we have at that point. Okay. Now, if we want x to be 0, y to be 1, and z to be pi over 2, then we can see what the value of t is just because t is, or z is t. So if we're saying z is pi over 2, then so is t. Okay. So let's say since z is t, the point 0, 1, pi over 2 occurs at t equals pi over 2. Okay, and indeed that's true. I mean, if t is pi over 2, then you have 2 times the cosine of pi over 2, that is 0. If t is pi over 2, you have the sine of pi over 2, that is 1. So all the components work out correctly. So it's very helpful that z is just t, of course. So now let's find the direction of our line, the vector to which it's parallel. So let's look at r prime of pi over 2. So that's negative 2 times the sine of pi over 2, cosine of pi over 2, and the third component is just 1. So the sine of pi over 2 is 1, so we have negative 2 times 1, so that's negative 2. The cosine of pi over 2 is 0, so we have 0 in the second place, and of course 1 in the third. Okay, so now we have a point through which our tangent line passes, we have a vector to which it's parallel, and so our parametric equations we have for x, you could say 0 minus 2t, but I'm just going to say minus 2t. For y we have 1 plus 0t, so I'm just going to say 1. Finally for z we have pi over 2 plus 1t, so we'll say pi over 2 plus t. And now I have equations of the parametric equations of the tangent line to this curve at this point. And with vector functions, like all of the things we learned in Calc 1 about derivative rules hold true here. So we see that we have the sum rule. If you take the derivative of a sum, that's just the sum of the derivatives. If we have a scalar in front of our vector function, it doesn't affect the derivative. The derivative would be c, that scalar, times u prime of t. We do have a product rule too. So here f is a scalar function, meaning that it takes a real number as an input and it also outputs a real number. So just like all the functions we saw before Calc 3, u of t is a vector function. We can tell u is bold. So here u takes a real number and it outputs a vector, just like the functions we've looked at in 13.1 and 13.2. But the product rule still holds. Derivative of the first times the second plus derivative of the second times the first. It even holds for dot products. Here u of t and v of t are vector functions, and we say there's a function created by dot producting them. But it's still the same rule. Derivative of the first times the second plus derivative of the second times the first. It also holds for cross products. So here we if we cross u of t and v of t, so we get a cross product, that's a new vector function because a cross product yields a vector, whereas a dot product yields a scalar. So we have derivative of the first cross the second plus derivative of the second cross the first. Finally, we have the chain rule. If we have a composition, so u is a vector function, and instead of being u of t, we input some other scalar function, just like in Calc 1 you would see f of g of t or something like that. So we have the chain rule, the derivative of the inside times the derivative of the outside function evaluated at the inside. That's called the chain rule. So all of the familiar rules from Calc 1 hold for vector functions. Integration is also easy. I mean, it's sort of, derivatives we do term by term, integrals we do term by term. So for example here, if r of t is 2 cosine ti plus sine tj plus 2tk, let's find the antiderivative of r of t. Now, when we do this, we have to understand that the antiderivative is going to be a vector function specifically. So our constant is also going to be a vector. Like you add the arbitrary constant at the end of an antiderivative. Here we're adding an arbitrary constant vector. Okay, so to do this integral of r of t, first I'm going to integrate the 2 cosine t that's in front of I. Then the sine t that's in front of j. Oops, forgot my integral. And finally the 2t in front of k. The antiderivative of cosine t is sine t. Therefore I have 2 sine t I. The antiderivative of sine t is negative cosine t. So I have minus cosine t j. The antiderivative of 2t is t squared. So I have t squared k. And then I have some arbitrary constant vector. And I indicate that this is a vector by putting an arrow over it. And that's it for 13.2. So sections 13.1 and 13.2 are pretty simple mechanically. We're just doing derivatives, integrals, and limits. And since we know how to do them in Calc 1, they're no different for vector functions. We're just doing them 2 or 3 times since we have 2 or 3 different functions. So, okay, goodbye.